solution to the initial value problem. All right, remember on our test we had like an initial value problem, which really was just amounted to we could find the constant of something, of the integral when we were evaluating it. So this one, it tells me my derivative is secant x. All right, that's what the dy dx means, the derivative. So if I want the integral, that means when I do the derivative of my integral, I should get secant. Now we know a derivative and an integral cancel each other out, right? So remember from yesterday, what variable were we usually using in here? T. And so that way we could go from a constant up to x secant t dt. Right, so then when you did this derivative, we get the secant x. Now technically, this constant here doesn't matter, but this is giving me a little bit of information. It's saying if x equals 2, then y equals 3. Right, so we need to be a little bit strategic about what we're putting here. We want to make our problem as easy as possible. We know if your starting and ending point are the same, so if my x is 2, I don't really want to figure out, what secant of 2 is. That's not ideal. But I know if I integrate from 2 to 2, what would that be equal to? 0. And then it would be really nice because then to get my 3, all I would really have to do is add 3 on the end. So if I give you that starting point, pick that as where to begin your integral. So if I look at this, the derivative is secant x. Okay, if I did the derivative of this piece from yesterday, we know that just turns into secant of x plus the derivative of 3 is 0, so that checks out. And if I plug in a 2, I get 3 out. The integral from 2 to 2 is just 0 plus 3 is 3. So we came up with the simplest scenario. We needed an integral to describe all of that information. Let's do, I'm going to go to this one, example 11. All right, fundamental theorem of calculus. What is the derivative of this? That's a review from yesterday. The only difference is, this time, the variable that I'm plugging in is t. So, t squared plus 25. We know the derivative and the integral essentially cancel each other. The only thing you have to look at is we're integrating up to a variable, so that would replace the variable in your expression. So just the square root of t squared plus 25. Look at this one. You guys take a second and try it. So it tells us g is the integral of this function over the interval 0 to x. So the derivative of g is the derivative of this integral, so it would be and we did talk about a couple variations yesterday. If it doesn't just go up to x, if it went up to like a 5x, what would you have to do? Plug in a 5x and then also multiply by 5 for the chain rule. We also talked about if it was flipped, if it went from x to a constant, what does that change?
Yeah, like, flip it to the negative front.
Right, when you flip it back, it puts a negative in front. So that was the first part of the fundamental theorem from yesterday. The second part was integrals, evaluating those, which we have been practicing in the previous section. So those two examples that I skipped were practice with that. Do we need to go back and do those, doing those antiderivatives? I'm not hearing a resounding no. What if we did, like this one before you integrate, what would you have to do?
5 x 1/3, subtract from the top.
Right. Think of this as x to the 1/3, and then we know we break apart. So x squared over x to the 1/3, you subtract exponents, so 5/3. Minus x over x to the 1/3, that would be x to the 2/3. 3 over x to the 1/3 would be 3x to the negative 1/3. And then could you guys integrate and evaluate from there? Okay. So you don't need me to finish this one? Just more practice of what we were doing before. Let's go ahead and do example 10. It's a little bit different. Find the total area bounded by the function f of x equals 9 minus x squared in the x-axis. Okay, the total area, that's kind of like saying the absolute value. Okay, so if I think about this, we want to figure out where this hits the x-axis. So it hits the x-axis at 0, -3, and 3. We know x cubed is a chair function, so it starts down here. It's just looking like this. So I'm finding we got total area from there. Now, when I'm saying the total area, that's like saying the absolute value. So I don't just want to integrate from -3 to 3 because that would have the positive area and subtract off the negative, right? But when I want that area, we're going to break it up. So we're going to go from -3 to 0. And then we'll go from 0 to 3. From -3 to 0, it's above the x-axis, so if I'm doing the absolute value, it doesn't change anything. But from 0 to 3, it was below the x-axis. So if I wanted the absolute value of that area, what would we have to do? So if we put a name in front or distribute it, -x cubed plus 9x. All right, so then if I integrate, antiderivative of x cubed is 1/4 x to the 4th. Antiderivative of 9x would be 9/2 x squared. Oh goodness, that is sloppy. Let me try that again. We're going from -3 to 0. This piece, the antiderivative, is the same, the signs are just -1/4 x to the 4th plus 9/2 x squared. So then if we evaluate, if I put in a 0, I get 0. Put in a -3, -3 to the 4th, 81/4. So after some calculating, we should get to our final answer, 81/2. Is that okay? Let's look at the very last example. Alright, so if I want to solve this initial value problem, it tells me the derivative of y is tangent. But then this information, this ordered pair is about y. Okay, so we need to find function y. So if this is the derivative, the antiderivative is just the integral, right? Alright, but I don't want to be stuck just doing tangent of 1. That's ugly. So this is where we use that fundamental theorem of calculus. Where should we start our integral? At 1. So whatever this number is, that's where we're going to start our integral. And we're going to go up to x. That way when you evaluate it, 1 to 1 would just be a 0. Okay, if you did this derivative, you just get your tangent x. So we've gotten this piece taken care of. Now when I plug in 1, I have to get out 2. If I currently plug in 1, I have 0. So how do we get a 2? Add 2 on the end. So if you make your integral start at your value here, then you can just add whatever that constant is to the end. And then we found a function that would work. Right. Again, we're leaving this as an integral because there is nothing that we know of that just has a derivative of tangent x, right? It's not a nice one. If I said the derivative was x squared, that's no problem. We could do the antiderivative and work it out. Since it's not nice, we can leave it in the integral and use the fundamental theorem of calculus to get there. Okay, so I want to stop now. I want to give you guys some time to work on homework. I might introduce the next section, and I won't get very far. I'm not giving you any additional homework, but I want you to work on that handout.